So today I wanted to talk about intermolecular forces, which are the forces in between two different molecules. But I want to get us started on the basics first. And I have demonstrations here, and I guess really as we learn more about these demonstrations, we're going to understand it more, hopefully. And it'll be a more interesting way of learning it, I think. So what we're going to do is today we're going to focus on water. And water, you already kind of know what it is. It's H2O, right? And I have a little model of it here. So I'm going to write down H2O is water. So you're all familiar with that. Because it's an easy example. It's very common. Covers like 70% of the Earth. Most of your body is made of water, all that good stuff. So we're focused on this molecule. This is the oxygen, the blue. These two white balls are the hydrogens. And then what are these? Anybody know? Let me draw the structure. So what I'll do is, instead of drawing just the formula, instead of writing the formula down, if you remember, oxygen has how many valence electrons? How many electrons does oxygen have in the outer shell? 6, right? So it's got, what, 8 total, but 2 in the first energy, 6, all right? So watch, 1, 2, 3, 4, 5, let's do a 6 here. And then watch how we're going to insert 2 hydrogens here with their 1, and then you're going to have a covalent bond here, you're going to have a covalent bond there. And look at how it lines up with this illustration. So what do those little fins represent? The electrons up here, right? So these are called lone pairs. These are your lone pair electrons. They're non-bonding electrons. So that's what this molecule looks like, and it has a bent shape to it. You see that? And so the reason why it's bent is you can think about it. It's pretty much VSEPR, which is valence shell electron repulsion theory. Pretty much the idea is that you have valence electrons up here, and what do negative charges and other negative charges do? Do they attract or repel? They repel. So all the negative stuff up here is going to push down on these bonds here, and it's going to form a bent shape. So that's why we say water is a bent molecule. See it? So this is a water molecule, a representation.
So this is a molecule of water. You can see the non-bonding electrons here, and you can see as I try to drag them closer, it'll automatically, the bond angles will change, but eventually they will become more steady. And you got a nice little picture of water here. You got the molecule geometry as being bent, but if you look at the entire electron geometry, you got a tetrahedral shape.
All right. Another thing is, what's the electronegativity of oxygen? Can somebody look it up real quick? I think hydrogen's about 2.2. You can confirm that with me in a second. So 2.2 is the electronegativity, which is how strong it wants those electrons, like how it's like a tug-of-war match for these electrons, right? So if you look at your electronegativity values for oxygen, I know oxygen's higher. It's like 3 point something, I think. 3.44. So, and now these are, depending on what your source is, these numbers might change a little bit, but it's about 2.2, right, for hydrogen?
2.20.
2.20, okay, so 2.20, 2.20. Now you can see which one's going to be pulling stronger, the oxygen or the hydrogens. Which one's pulling on those electrons stronger? The hydrogens are the ones that have the less number, right? So they have less, they're weaker. So remember, the number represents the strength of how much it wants electrons. So the one with the bigger number is going to be pulling harder. Good with that? So now the electrons are going to be pulled towards that oxygen. And this is going to generate pretty much what we call a permanent dipole moment. What that means is that you have some positive charge here. So you have partial positive charge here on this hydrogen. And then where the electrons are being pulled towards, isn't that going to be more negative, right? So you have partial negative charge up here on this oxygen. Same thing's going to happen over here, partial positive, and you're going to have this dipole moment here. So here's the general idea. Overall, you have a negative side of the water molecule, and you have a positive side of the water molecule. Do you agree? And so we call this, these are both polar covalent bonds, because if you look at the electronegativity difference here, it's not quite strong enough to be ionic, but it is strong enough to be a polarized molecule. And so even though we would say that overall this is neutral, the charge is separated. So that's what we mean by polar, right? Like, for example, somebody who is bipolar has polar moods, right? And then somebody like the pole, like north and south pole, you're separating. Here we're talking about charge separation, positive and negative charge separation. All right, so what we do is we call this a polar molecule. And so we say that water is polar. All right, one reason we say it's polar is because of the charge distribution here, like the separation of charge. And the other reason why it's polar is because it doesn't cancel itself out. So what I mean by that is this is carbon dioxide. This also has polar bonds. All right, so we can do the same thing for carbon dioxide, like this, which is something that as you exhale, you have coming out of your lungs. And so we got 1, 2, 3, 4, 5, 6, 7, 8, something like that. But notice up here how the oxygens want the electrons more, but do you see how they're pulling in opposite directions? So it cancels itself out. So you need really two things to be a polar molecule. You need a charge separation, like a polar bond, pretty much. And you also need it to be not symmetrical, because if it is symmetrical, if it's pulling in opposite ways, then it can cancel itself out. So now you understand what a polar molecule is, right? So that's really the first step. So we understand this. Next thing, now we need to understand when we take one of these molecules, it actually doesn't make sense to talk about one of these molecules in here, does it? Because clearly this is way too blown up. This is a model. One, like, in other words, we're starting to ask the question, how big is this molecule? So this right here is a certain amount of water. It's a pretty easy, simple demonstration. It's approximately 18 milliliters of water. So 18 milliliters of water is how many grams? I'm going to say the density of water. You remember what the density of water is? So here's like the first thing that we did today. Let me label it number 1. So the second thing we're going to do for the day is the density of water. Do you remember what that is? How dense water is? Yeah? Yeah, 1 gram per milliliter. 1 gram per milliliter, and a milliliter is a centimeter cubed, or a cc here, cubic centimeter. Bottom line is, pretty much what we mean by this is that if you have water in general, then it's going to take up it's going to have 1 gram of water, which is the mass, in 1 milliliter of space. So that's how dense, how packed it is, right? And so if we look at that, and I just told you that I have about 18 milliliters of water, that's going to be about equal to 18 grams of water, right? So that's how much water I have in there right now. So what is the significance of that? Well, we have to understand something, that pretty much the molecule is so small. You guys remember how small it is? We watched those videos.
So if an atom was the size of an orange, the orange would be the size of the entire planet Earth. As you can see, the scale of the universe pretty much spans from an atomic nucleus, which is crazy small, all the way to, the size of the galaxy and the entire universe. So we really are only observing a small, small part of the universe on a daily basis. And our perception of the world gathered through our senses is really just forming our reality, which is quite small.
Pretty much what I'm getting at is that the molecule is so small that we actually need a new number to define it. It's called Avogadro's number. So Avogadro, which is a scientist, he came up with this idea. He's like, okay, well, this is a pretty reasonable amount of water that I want to talk about. I don't really want to talk about too much smaller than that. And so if I wanted to count up all of the molecules in there, I would say that I could represent that as a new quantity. It's called a mole. And so we're not talking about the mole like on your face, or the mole like the animal, or the mole. Is there any other places that you hear the word mole, like your molar, like your teeth? We're not talking about that. We're talking about a new quantity in chemistry. And so what we say is that there's 6.02, and you can add another 2 if you want, 6.022 times 10 to the 23rd molecules or particles per mole. right, that's Avogadro's number. And that's a ridiculously big number. Let me just give you an idea here. So 6, and then I have the 0.022. I need to move that decimal place over 23 times to the right. So let me start writing zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, 20. Okay. Let's start moving. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So let's count the commas. Right here, now we have thousands, right? We have millions, we got billions, we got trillions, we got like quadrillions, and after that is pretty much sextillion. So you have a ridiculous amount of molecules for every mole. And so what we're saying here is that this amount of water is actually really important. And I'll show you from the periodic table real quick where we get to this 18, and then you'll more fully understand. So stay with me just for a second. With water, how many hydrogens do we got? 2, right? And each of them weigh, if you looked at the periodic table, each of them, if you look at the mass on the periodic table, each hydrogen, we have 2 of them, right? So we could say 2 hydrogens weighs how much? And then we have 1 oxygen. So how much does a hydrogen weigh on the periodic table? Check that out. It's the red number on that one, or you have your own.
1.008.
Yeah, so it's about 1.008, something like that. So I'm just going to round it to 1. So this weighs 1. And we'll forget the unit for a second. And then oxygen is 16. It's like 15.999, whatever. So about 16. Now this is 1 times 2, right? Because there's 2 of them. And so we get 2. Now, what's 16 plus 2? 18. And so there's that number 18 coming back again, is because water weighs 18 grams per mole. That's called the molar mass, all right? So the molar mass of a substance can be found just by adding up the weights of the elements in the chemical formula. Basically what we just found out is that 18 grams of water, which is about the same as 18 milliliters of water, which is about what I have here, represents 1 mole of water. Do you agree? This is 1 mole of water. So instead of saying I have 602 sextillion molecules of water in here, which is a crazy unheard of number, I can just say I have 1 mole of water. Instead of saying you have 12 eggs, what could you say? I have a dozen. Instead of saying you have 100 years, what could you say? A century. Or 10 years is a decade. Or 100 centimeters is a meter, right? So bottom line is we have units. This is a new chemistry unit that we have for understanding how much of something that there is. So that's called the mole. All right. So far we've talked about what water looks like. We talked about its polarity, and we talked about this new idea of a mole. All right. You got to be comfortable with that. The next thing we're going to talk about. So now we know that there's a ton of these water molecules. Like pretty much, you remember my little. Where's my little thing? Right here. If you put this in here, like there are so many of these molecules in here, it's crazy. There's like 600 million, trillion, billion, quadrillion, whatever you want to call it. All right, that's how big that number is. It's crazy. That's how much is in there. Okay, so now we go over to the next one. A couple other things. How does it relate to energy? Do you remember how this thing broke? It says thermal shock on there. How did this break? So it was very hot. And when there was actually liquid metal in here. It was very, very hot, and somebody put it down on the table, and then they squirted some water in it, and cracked. Have you ever heard of that happening? So you have something that's very hot, and then especially when you have water, what happens is, in this case, it was very hot, and when you squirt the water on it, water is really good at sucking up energy and storing it. We could say it has a high heat capacity. And so that's one of the other things about water that's really awesome is that it does have a high heat capacity, and that's why we use it as like a coolant. Even like your radiator fluid, like antifreeze, that's going to be a lot of water in there. You could actually just use water, but it's probably not recommended because antifreeze doesn't really freeze as much as water, so you're not going to want to use just regular water. Also, water is associated with increased oxidation, like rust. Bottom line is, you've heard of water cooling systems before. Water is really good at sucking energy out of things. So when you have an object that has a lot of energy and then you cool it down really quick, it'll actually contract, and that thermal contraction is, or thermal shock, it shocks it to the point where it just can't do it anymore. It has to crack. The whole thing cracks nicely like this. So that's a pretty good illustration. So that is, how does this stuff relate to energy? We got another example right here. I got a question for you real quick. It actually does have to relate. It relates to this right here. When you're hot in the summer and you put a fan on yourself, does it cool you down? Is it because the temperature's lower? Isn't it just blowing more hot air on you? How is it making you cooler? Have you ever thought about that? How does a fan, which is just blowing the same temperature air on you, making you cooler? How does that make any sense at all? Have you ever thought about that? I'll give you another hint. When you get out of the shower and you're wet, or get out of a pool, all right, you have all the droplets on you, and you walk out of the shower, do you feel cold? Why? It's the same question, isn't it? It's also the same question, a very similar question, why does this bird keep drinking? Same reason. So it has to do with evaporative cooling. So in other words, as water evaporates off of your skin, or as water evaporates off of this felt here on this drinking bird, or as water evaporates, like you know how the fan, water is going to evaporate quicker off of your skin. Your sweat is just water, isn't it? So when you sweat, it's mostly water because your body's trying to cool down. Well, you're sweating and then it's evaporating off your skin, cooling you down. It's awesome. So this has to do with the energy too. Pretty much as things evaporate, what's happening to the energy? What did we say? When water turns from a liquid to a gas, it makes the thing behind cooler, right? It's called evaporative cooling. So there's clearly some energy going on there. Okay, so that's not fully describing this, but this is, I don't want to go too much into more detail about this. Okay, the next thing is this. How does that work? We're almost to the good stuff. We're getting more and more complicated, I think, possibly. What about this? How does that work? So what's in there? Oil and water. Now there's other stuff in there too, like I think I had some alcohol and soap and food coloring. Obviously this is not pure water down here. But bottom line is it's mostly water and oil. All right, so why are they not mixing? What have we said? So what's your current understanding on why they're not mixing? Yeah? You definitely could say that because things have different densities, and we know that's another reason why, like for example, ice floats on water, because as water freezes, it gets bigger. It has pretty much as it gets bigger, it's less dense, and then it's able to float on top of the water, which is why we have ice skating and all that. But let's not talk as much about that. That's why the oil is floating, right? So we can definitely say the oil is less dense than water, right? But why are they not mixing? Because just because they have different densities doesn't necessarily mean they won't mix. So why?
This is shears. It's something kind of like this, but they have more to do with like a cell. They have like these little things on top that will let something in.
Okay. It does have, well, are you thinking about like a cell?
Yeah, I'm thinking about like a cell.
Okay, and every cell pretty much has a membrane. In other words, a border to the cell, right? And have you ever heard of the phospholipid bilayer?
Mm-hmm.
So that is a lipid or a fat, yeah. So that is very similar to oil, which is kind of a fat, right? A lipid. So this oil is, you can also, maybe you've heard of this, hydrophobic. So it fears the water. But a better way of describing it maybe is that this is nonpolar. So the oil is nonpolar, and the water is polar. And have you ever heard of like dissolves like? So like dissolves like. In other words, if I have something that's polar, it's going to be dissolved by water, which is also polar. We said water was polar. So water's not very good at dissolving something that's not polar. But water is very good at dissolving stuff. which is why it's called the universal solvent. It's pretty much like that's one of the reasons why water is so important, is because water's really good at taking stuff and dissolving it and pulling it apart and doing all sorts of awesome stuff. Most of your body's water. When you urinate, most of your urine is water. When you sweat, most of your sweat is water. You are made up of a lot of water, okay? So another thing is, like, if I were to put oil on my hands, would it be hard to wash my hands? If I had this, would it be hard to wash my hands? So this is a degreasing soap. Pretty much like this Dawn dish soap, it says it helps save wildlife. Bottom line is, this stuff right here, Dawn does not sponsor me, but bottom line is, if I were to get oil on my hands or butter on my hands, it would not get off very easily just by rinsing it under the water, would it? But if I start to use a degreasing soap, it would. Why is that? Because water is not really good at bonding with something like oil. We can see that right here. But what the soap does is it forms a bridge. So imagine the soap is in the middle. So the soap has something called surfactants in it. And the soap bonds to the oil on one side, and then on the other side it bonds to the water, and so now you can wash your hands. So when you use something like this, you're able to actually get that off of your hands. So that's a pretty cool application of what we're talking about. This is all real life stuff pretty much. So now we get into something else. Now we get into, so we know what polar and non-polar is. I don't really have to do anything more up here so far. Now we get into something else. I kind of have to start getting into some more stuff pretty soon, but let me just do the series of 3 right here, and then we'll get into the last little bit of stuff we have to do. So for this, you'll notice how one of them is full. Now if I fill this up a little bit more, you see that? And you saw it before. It's starting to go above the actual top. What is that all about? Look at that. I can do it with the other ones too. These guys evaporate over time, so I have to fill them back up. But you notice how I'm able to actually fill them up higher than the top, which is pretty crazy. Look at that one. That's awesome. And so, wow. How is this possible? Now, eventually it'll start to fall down. How could you describe that? That's mostly water, by the way, right, with food coloring? Mm-hmm. So just think about the water, because if I just had regular water, it would also do that. So why is it doing that? Think about that. Yeah? Yes. Did you hear that? It's actually a really good description. So she said, it's because there's a reason why I went over this to start with, right? It's because the oxygen has a partially negative charge and the hydrogens have a partially positive charge, and there's a whole bunch of molecules. That's why I just talked about this with the ridiculous number of molecules that you're seeing right here. So there's a ridiculous number of molecules packed in there, and all of them are attracted to each other. And that's also called cohesion. Have you ever heard of cohesion and adhesion? So cohesion, it's attracted to itself. Water sticks to itself. If you have one water molecule and another water molecule, they're both polar and they're going to align themselves nicely and they're going to attract. All right? So let's illustrate that. I'm just going to give you a simple illustration. This will be the last thing that we do, I think. So this will be like, okay, we have one water molecule. I'm not even going to necessarily draw everything, but here's the basic idea, right? So you would say that this has a negative charge, right? And then you could line up with something like this. You have another water molecule, and this is positively charged right here, so can't those two things interact with each other and attract? Positive and negatives attract, right? We know opposites attract, so that's good stuff. It's also called surface tension, so you have some tension at the surface, and it's trying to pretty much ball itself together, and eventually it'll get too much. Eventually, the cohesion, you can kind of break it, and then it'll eventually start dripping out. It's not infinite attraction, right? It'll eventually break down, but that's pretty awesome. So we know water is pretty high surface tension. And so a lot of properties, this gets me to my next point, like water having a high heat capacity, water having a boiling point, melting point, water having high surface tension. A lot of the properties of a substance has to do with how the molecules of that substance interact with each other. Because right? Clearly you're never just going to have one molecule of a substance. When you say, oh, I have some bleach, or I have some acetone, or I have some caffeine, or whatever, there's going to be a bunch of them. There's not just going to be one molecule floating around, right? Molecules are so small, like we were saying, you're always going to have more than one usually. Okay, now here, What about this? How does this work? There's a pencil going through here. Now watch me squeeze this. You see this, Bobby? Watch this. I'm going to squeeze it. Ready? It leaks, right? So if I squeeze it, it leaks. So I did not seal this. There's no, caulking or glue or anything like that. I literally just took a pencil and poked it through a bottle, and it's filled up with water. So why is this not leaking? That's pretty crazy, right? One thing I also noticed is that if you look in there, I doubt you're going to be able to see it really good, but has anybody ever heard of like the refractive properties of water? So like if you're going fishing for a fish and you're trying to throw a spear at it, you're not going to actually want to aim directly at the fish, because the image of the fish is redirected because light bends as it hits the water, because the index of refraction of air and water are different, so it's called refraction. So we're not really talking about that right now, but that's also a cool property of water, right? How it interacts with light. So we talked about that, which is pretty much spectroscopy, how light and matter interact with each other. But that's not really what we're talking about. We're talking more about why it's not leaking. So why would it not be leaking? I can leak it like that. Same reason, isn't it? It's stuck to itself, right? And there's another reason too. So if I go like this and I unscrew the cap, what do you think is going to happen? Well, let's see if I can get the cap undone, because it's on there pretty tight. But if I get the cap undone, do you think it'll leak if I unscrew it? Okay, I got the cap undone. Here we go. And so I can let it sit there. You can actually see it leaking. See it? I'm not squeezing it, but it is leaking slowly. And if I leave it like this, trust me, it'll be gone a lot quicker. Right? So, why is that? What does the cap on and off have to do with anything? Yeah? Pressure, yeah. Do you know the atmosphere that we learned about? The atmosphere is allowed to push its way in there, right? So if I put a cap on here, is there still air at the top right there? And that air is not allowed to interact with the environment. So the atmosphere can't come in and push that water through the leak. So if we close it off, there's actually kind of like a vacuum in there now. So there's some air, and it's a low pressure environment. And so it's going to be sucking up on that water. So there's actually two reasons why this is not leaking. One is because of the vacuum environment up here, and two, because of the surface tension and the cohesion here. Last one, but not least, definitely not least. There's a reason I saved this one for last. Okay, so I have an Alfredo jar, okay? And this one, I just grabbed it from home. You could do this with any jar that you want, pretty much. So you grab a jar, you fill it up with water, starting from scratch. Now that's not pure water, it's tap water, but then I'm gonna grab like an index card, okay? I'm gonna put the index card on top. Have you ever seen something like this? So check this out. So I'm gonna see if all that water can be held in place by the index card. It might leak a little bit, so I'm gonna go over the sink. It's leaking a little bit as it starts to saturate that index card. Ready? The moment of truth. All right, look at that. Isn't that awesome? So the water is being held on there. It's kind of the same type of reason as the other one, right? Maybe? What about this? You ready? What do you think will happen when I take this one? All right, if I'm very steady, maybe it won't. Ready? You see that?
It's plasticky. There's plastic on there or something.
Look at that.
There's no way.
Now, if I shake it and I disturb it, it'll definitely leak, right?
What? Dude.
So, what's happening there? That was the best for last right there. So let's try it again.
So mad.
I want you to watch the whole process again. See if you can identify what's going on. All right, you ready?
Can you use one of my index cards so I can make sure there's like...
Sure. Yeah. Give me one of your index cards. So we're going to use an index card from the audience. Okay. Are you sure? Now, maybe we consulted with each other before class, and this is just another magic index card. No, we did not. All right, so I'm going to fill it up. Notice how I'm filling it up. No big deal. I'm going to put the index card on top. Okay, the one that she just gave me. And then I'm going to slowly tip it over. Watch it not work now. All right. Non-magic index card. First step. Second step. All right, so what is the trick? And then if I disturb it, you see how it's pretty, if I disturb it, then it'll definitely come out. So, what's going on? Anybody know? Anybody have any guesses? What'd you guess?
It's the same thing as the ball. There's nothing interactive. It's not going to push out.
So do we agree gravity's trying to pull it out, right? But we also agree that, oh, let me show you this. Watch this. Let me see if you can explain this. Do you think we need the index card at all?
No.
Ready? If I do it quick enough.
Oh my gosh. Wait.
All right.
Is it because of the air at the top?
So
Like the
it is
bubble?
partially because of that air at the top. So the air at the top is a vacuum. And it can't come down because the atmosphere can't get in there to push it out. And if I tilt it, watch the bubbles come from the bottom. So the bubbles from the atmosphere, they're going to force their way in. See the bubbles coming up? And then it empties.
Is that the same as like centripetal force where it like extend something?
So centripetal force is the force that holds something in circular motion, which pretty much the opposite of that is like this imaginary centrifugal force or whatever. The idea that masses are going to get farther away, like a centrifuge, like when they separate the components of your blood. It's a little bit similar to that, but I would say that number one, you have to describe this as being a pressurized system. Like, in other words, there's low pressure on the top, which is kind of acting like a vacuum to hold against gravity, because clearly gravity, we've all learned that when you drop something, it falls. And water obviously has mass to it, right? It's 18 grams per mole. So we know water has weight to it, and we know that water wants to go down, so the only way it's not going to go down is if there's something holding it up. Well, in this case, there's actually two things holding it up, so you actually only know half the story. You understand the top, right? You're probably going to be mad. You don't understand the bottom. You see it?
I knew.
So there's a screen here, glued to it.
I saw something.
That's the
there.
only
It was
way.
just a weird little-
I was gonna go home.
I've actually seen videos of people like trying to do this, and I've seen a video of somebody turning the bottle upside down and like grabbing it out real quick, and all the water just stays there. And I'm like, there's no way. It's just maybe some tricky footage there, but it is very cool. I mean, even with this on the bottom, because we know, like, now that you know how it works. Okay, you have a screen there; it's glued. That's the reason I was covering it like this a little bit as I was pouring it. But the idea is, you know, it can go through the screen. We know it can come out of the screen. So it's not the screen that's doing it all by itself. The screen, which provides a surface for it to have tension on. So you do have that surface tension cohesion happening, for sure. It's allowed to now have a surface. Without the screen, it would not work. So you need the screen. But you also need that other part, where you need to turn it over quickly in order to get that effect. It was pretty awesome. And I just do the index card just to make it more fun. I don't need the index card. But that's pretty cool. Now watch one more time. The air comes in from the atmosphere, and it pushes that water out. The air comes in and takes the space up above, and is able to come out. Awesome. So based on that, the last thing we got to cover. So hopefully those demonstrations and stuff. Hopefully that gives you some context and application. Last thing we got to do is this. We got to continue on what types of forces in between molecules are there? Because there's actually multiple different kinds of forces. So we actually already described the one type of force between molecules, which I would call dipole-dipole. Dipole-dipole, most people call it that. So this case specifically is called hydrogen bonding because it involves hydrogen. And this hydrogen is attached to a really electronegative atom like oxygen or fluorine. So whenever you have a super electronegative atom like oxygen or fluorine that have like above electronegativity 3. So they really want the electrons, and if anytime that that's attached to a hydrogen, you have the possibility of hydrogen bonding, which is pretty much the strongest form. So this is a strong form of dipole-dipole. In other words, didn't we say we have a dipole here? Pretty much the overall dipole, wouldn't that be something like this, the overall dipole here? And the overall dipole here would be something like this. So the positive side of this molecule, the positive side of that dipole, is going to be attracted to the negative side of the other dipole. So that's called dipole-dipole because there's two different dipoles attracting each other. It's called dipole-dipole. That's the first kind. The next kind, we just got to learn two more, all right? Stay with me. The next kind, so let's say this is A, all right? And then B is going to be, let's say we have an ion. Remember how, like, let's say we have sodium chloride, which is table salt. Let's say you put table salt into water, what does it do? Dissolves. It's an ionic compound. Ions, which is ionically bonded, pretty much they're so selfish that they just take the electron all the way. It's not partially positive or partially negative anymore. It actually has a full positive or a full negative. We call that an ion. So is it possible that we could have an ion attracted to a dipole? So we know that ion-ion is pretty much ionic bonding, isn't it? But what about an ion attracted to a dipole? That would be ion-dipole. So the ion dipole here, I guess you could, say ion-ion would be a different kind, but that's just ionic bonding. But we're really talking about ion and dipole. So what do I mean? Let's look at a sodium. Sodium would have what type of charge after it dissolves? Positive, right? So we have positive sodium, and if you look at how the water molecule is going to line itself up, the water molecule is going to take the negative side, so we have a partially negative side of the water molecule overall, and so you kind of have this thing. So here's your dipole, here's your partially positive side of the molecule, and so we have the negative side of the dipole attracted to that positive ion. And so the oxygens are going to surround that sodium and just rip it apart. Same thing with the chlorine. The chlorine, though, is going to be attracted more to the hydrogen side of water. So that's your second type. You good with that? We're talking about intermolecular forces, which is pretty much all these demonstrations were in an attempt to teach you about intermolecular forces, which are the forces in between molecules, which clearly we said that if we have anything, it's probably going to be more than one molecule. And if you have more than one molecule, which is pretty much nothing because it's so insignificantly small, then you're going to have some forces between them. Like tape, right? If you take a piece of tape or a Band-Aid and you stick it, wouldn't that be a strong intermolecular attractions there, right? So a lot of stuff in the world can be explained by this. That's what we're learning about. So A, B, and then C. Last one is the hardest one to understand. Now these ones are your temporary. So these ones are, I would say, your induced. It's an induced attraction. I guess you could just say that. Induced attraction. Because there's different kinds of this. But what I mean by induced, what does the word induced mean? Anybody ever heard of induced labor? It's a thing, right? During pregnancy, what does that mean? Yeah? It forces the pregnancy. So induced is pretty much to bring about, like, it's happening, and in this case it's a temporary thing. It's just something that's induced to become an attraction, but it's not always an attraction. It's a temporary thing. So this is the weakest form. So we're not talking, remember guys, real quick, these are intramolecular forces. These are intra with an I-N-T-R-A. These are the forces between atoms within a molecule. We're talking about intermolecular forces now, which are the forces between molecules. But out of the forces that between two different molecules, these are the weakest. All right, these are just temporary attractions. Let me give you an example. Sometimes they call these ones that I'm about to talk about London dispersion forces. There's a lot of fancy names for them. Bottom line is, if you had a molecule that's usually not polar, let me give you a perfect example of something that's pretty much purely covalent. The nitrogen that you breathe, 80% of the air. We've talked about this before. Isn't that a nitrogen bonded to another nitrogen? So is there any electronegativity difference there? they both want the electrons the same because they're the same exact element, right? So is this a polar molecule? No, it's strictly nonpolar, but temporarily it can become polarized. So what I mean by that is that these electrons are moving around, right? These electrons are not just staying in one little place. They're not just little, particles that behave themselves. So every now and then, part of this molecule, let's say the electrons, let me do it in blue. You ready? This is the hardest one to understand, I think. If you have more electrons on this side temporarily, then it would be temporarily negatively charged, right? And if on the other side, the electrons decide to temporarily spend a little bit more time on the left, that's going to leave this side with a partially positive charge. And so you end up with a temporary dipole. And that temporary dipole can then attract another temporary dipole. Can't you have another one of these guys floating around there like this? N triple bonded to an N. Again, here's another one. And you got two of them, and let's say that this guy has that partial positive and this guy has that partial negative. Notice how now we have an attraction between these two things. Positive attracts negative. This entire unit on molecules and bonding has to do with opposites attract. All right? Opposites are always going to be attracted to each other, but how that attraction is coming about, that's where the classification comes in. So that is one type of induced attraction. There's other types of induced attraction too, and you'll see that on your notes.
So these are the three main types of intramolecular forces, the forces that hold a molecule together. You have the ionic bond, where you have a transfer of an electron and you have attraction between ions. Then you got the covalent bonds, which is more like a sharing of electrons, and then the metallic bonding, which is kind of like a combination of the two. You got the metal ions and these delocalized electrons that can go all over the place. It's like an ultimate form of sharing. Then you got the non-bonding or the intermolecular forces, the forces in between two different molecules. You have different ways that this can be brought about. It could be an ion dipole, a hydrogen bond, which is pretty much a form of dipole-dipole. It's like the strongest form of dipole-dipole. You can also have different induced attractions. So the ion-induced, the dipole-induced, or the dispersion, the London forces.
So, bottom line is you got three types of intermolecular forces. You got forces between dipoles, you got forces between an ion and a dipole, and then you have these weak induced temporary attractions that can exist as well. Those are the three main forces that can exist between molecules, right? So, I think we're good. Any questions on that? Awesome.